Hello all, my name is Max Cooper. I'm from the Steel Construction Institute, and welcome to today's webinar on the combination of actions. It's a topic that's perhaps not the most exciting, not the most thrilling topic, but it's one that we do get questions about. So we put together this presentation or this webinar to hopefully clear up some of those questions. So a quick overview of what we're going to cover today. It's the title of the presentation is Combination of Actions. Actions, what we might have called loads in the past, but now we're all fluent in Eurocode speak. I'm sure everyone's familiar with the term actions. We'll be looking at the combination of actions in accordance with EN 1990. And since we're designing, well, I'm assuming we're designing for structures in the UK, we'll be focusing on the UK National Annex. We have ULS and LSLS combinations, so that's ultimate limit state and serviceability limit state. I'm sure everyone's familiar with what those terms mean. I won't dwell on them now. But we'll also be looking at slightly more exotic considerations, such as accidental and seismic load cases. Accidental actions, certainly in my experience, they crop up more frequently than you might expect. Even perhaps for, let's say, standard buildings. Seismic is not something we're going to dwell on too much because we don't typically have to design buildings for seismic. We don't have seismic design loads in the UK, apart from perhaps for nuclear power stations, so I'm not going to dwell on that. There'll be a section on reduction factors, which I would encourage everyone to use, and hopefully by the end of today's presentation, you'll know why they can be a benefit in reducing loads quite significantly. And obviously, with reduced loads, we get more efficient structures, cheaper structure, more cost-effective structures, and structures with lower embodied carbon. So that can be of great benefit. We'll then cover brittle fracture. It is it's the SCI's view very strongly that the selection of subgrade is the designer's responsibility, and there is a component of that assessment that requires the designer to look at a combination of actions. So we'll cover what that means in today's presentation, and then finally we'll look at the combination of actions for cranes, which can be quite complicated, and also there's a sort of slightly surprising part that comes out of the Eurocodes on that. So we'll come to that right at the end. So starting with EN 1990, we have three different categories of combinations of actions. We have fundamental combinations, so that covers permanent, persistent, and transient situations. That concerns every structure, so I'm hoping that everyone on this call will be familiar with what that means. We'll consider combinations for accidental situations. As I alluded to in the previous slide, they crop up perhaps more than you might expect, but certainly not for every structure. And then finally, there are combinations for seismic situations, which we, as I mentioned before, we don't typically need to consider in the UK. So if we now look at variable actions, what's the sort of various parts of the nomenclature mean? So going from the top, we have capital Q, that would represent a concentrated or point load variable action, and lowercase q would represent a more distributed load. So a couple of examples of these, you might want to consider a distributed floor load, for example, for an office. But if you're designing a handrail, you might be more the distributed load would be represented by the lowercase q. But if you were looking at, for example, a handrail and you wanted to look at a point load on that, then you'll be considering the capital Q. We use the subscript K to represent what's known as the characteristic action. And we find those characteristic actions for the different types of loading from the EN 1991 suite of codes. So it's EN 1991 Part 1 for floor and roof loading, Part 3 for snow loads, and Part 4 for wind loads. And the characteristic value of these actions represents the 1 in 50 year event. So if it's a wind load, it's a load that we would expect to happen fairly infrequently. So if we now move over to the left-hand side of the screen, I'll just get my pointer up so everyone is clear what I'm looking at. So we now have, we have 4 different values that the Eurocode may wish us to take. So we've described that the characteristic value is this 1 in 50-year event, but there are also 3 different other values that the Eurocode will call for. So the first one to consider is what's known as the combination value, and this takes a reduction factor known as psi naught. So to determine the combination value of an action, we consider psi naught. If we want to look at the frequent value of an action, we use psi 1, and if we want to use the quasi-permanent value of an action, psi 2. So you'll see that for each different load type, we start with a characteristic value, so that would be qk, and then depending on whether we want to look at it at the characteristic level or some other level, that could be combination, frequent, or quasi-permanent, then we multiply it by a different psi factor. And the psi factors are not something that the designer needs to has any choice on, I should say. The psi factors are given by the Eurocode, so there should be no doubt in which psi factor you should be using. They should always be specified in the Eurocode or the UK National Annex. So a few things to just point out here is that once we start with the characteristic value at qk, whenever we multiply it by a psi factor, that psi factor will either be equal to 1 or less than 1, and most commonly it'll be less than 1. And we'll go on to what that means later. So what do these sort of different load levels represent? So we've got a sort of simplified load history plot on here, and I suppose you could say that this is supposed to represent a 50-year period. The characteristic value is really sort of the maximum value you would ever expect to see. So it would occur very infrequently, and as we go down the different load levels, we would expect that load level to happen more frequently, and at a lower level. So we go from the top, we've got the peak value as the characteristic value, and that's shown in red. And then at the bottom, we've got the quasi-permanent value, and that's shown in green. So characteristic, peak value, happens very infrequently. Quasi-permanent is you can see from the length of the green line going from left to right. If I show here, that load level is present almost all the time. So again, we're looking at variable loads here. So for example, a floor load. But when we're looking at the quasi-permanent load level, that is a load that we'd expect to see all the time. An example would be in an office. Let's say an office load level would typically be taken at 2.5 kilonewtons per meter squared. That would be the sort of peak load. But there are, and that would represent quite a few people standing in a certain a given space. The quasi-permanent value would represent the load that's always there, and that perhaps in the case of an office would represent things like the furnishings and the printers and that sort of thing. Now, that's not to say it's not a conservative estimate, but that's what we're trying to define there. So when would we be interested in the quasi-permanent load level? Well, the time I've used it most frequently is when we're looking at creep. So certain materials such as concrete and timber creep, and that means that they have a time-dependent component of their deflection. In order to calculate that, we need to know the load they are subjected to all the time, because they will not be, if there's a variable component, they will not be, it will make no difference to the long-term deflection. So that's when the case we would use quasi-permanent load level, and we would use psi 2. So the values for the different psi factors are not the choice of the designer. They should come from the National Annex. And if we have a quick look, sorry, I'll come on to that later. So looking at different ultimate limit states, in EN 1990, we have 4 different categories. We have EQU, which represents the consideration of equilibrium, and I would suggest that this is fairly uncommon for most common structures. This is something you'd be looking at if you're worried about overturning or sliding. We have the SDR combinations, structural failure. This is what we use hopefully every day. Well, this is what every structure would be concerned with. We have GEO, which is geotechnical failure. So obviously that would be combinations we would look at for foundations. And we have FAT. These are load combinations for fatigue failure. And again, that'd be something that we wouldn't typically consider for most structures, but we certainly would be interested in that if we're designing, for example, bridges. So focusing on the STR load combinations, we have two options that are given for STR. We have equation 6.10, or we have the most onerous of 6.10a or 6.10b. So let's just go through those in a little more detail. 6.10 is a single expression, hopefully quite simple to use, but will give you a slightly more conservative value. Expressions 6.10a and 6.10b, slightly more involved. There's two expressions to consider, but hopefully that slightly increased workload will result in a lower design value and therefore a more economical structure. And critically, I think we would always suggest that the designer should use 610A and 610B. If you're the steelwork contractor, obviously it will give you a more economical structure. But also, if you're just any designer who is concerned with saving the planet, then obviously a lower design value for the loading will allow you to use less material and less carbon. So I think we believe here at the SCI that everyone should be using 610A, 610B. One thing you may not be aware of is that the choice of using these different expressions is something that is permitted or not by the national annexes. We are fortunate in the UK that either is permitted, so that we can use 610A, 610B, but there are some other countries, for example, I believe France, that they can only use 610. So we'll get on to comparisons later, but what we'll find is that 610, a little bit more conservative, slightly easier, but in general, 610, it's not much work, much additional work to use 610A and 610B, and it will give you a benefit. So here's 610, and we're going to start with we'll build up in steps here. So I'm starting first of all with the more basic of the expressions, which is equation 610. I've also only considered one variable action, and we'll get on to why I think it's easier if we start this way. One thing you can say is that most design situations really only need to consider one variable action. And when I say most, I mean the most common situations, which is, for example, if you're designing a floor, you're not going to be considered, you want to consider the occupancy load, but obviously it's going to be an internal space, so you don't need to deal with wind or snow. So I think it's helpful to just build up using just looking at a single leading variable action. So let's start with looking at the components of the expression. First of all is we have the addition symbol. In this context, all this means is that we are combining these actions, so we're just adding them together. We now look at the term on the left. We have the summation, so that's the summation of the different components of the permanent load. So, for example, if you're looking at the self weight of the structure itself and potentially the superimposed dead loads, you could represent them by the subscript J. And these are multiplied by the partial load factor gamma G, and gamma G is taken from the UK National Annex, and it's taken as the value of 1.35. So that's the summation of all of the permanent loads. If we now look at the expression on the right-hand side of the expression, we have the leading variable, so variable load. So we have QK, so that's the characteristic value of the variable action, and then we multiply that by gamma Q. And again, we go to the UK National Annex and we find that gamma Q is 1.5. So hopefully everyone's familiar with this expression. This is the combination of actions in its most straightforward term, and one I would suggest that many people use every day. If we put that all together, we see it really is quite straightforward. 1.35 times the permanent actions, and in combination with, so added to 1.5 times the variable actions. So that's the case where we have a single leading variable. If we now want to look at cases where we have multiple variable actions, so that might be imposed and wind together, sorry, snow and wind together, we see the first half of the expression is exactly the same. We have the 1.35 times the permanent actions and 1.5 times the leading variable actions. We now introduce other variable actions. So we have, again, QK, so it's the variable actions at that characteristic level, but then multiplied by psi factors. And we discussed, and this is psi naught. So as I discussed before, the designer should not be making any decisions about what to use. Is it psi 0, psi 1, or psi 2? It is in this, it's specified on the Eurocode, it should always be psi naught. So we have the summation of all the other variable actions at the using the combination factors and the partial load factor gamma q, which again we saw before was 1.35. So psi naught is the combination factor, and it is associated with the type of action. The values come from the UK National Annex. They were specified in the Eurocode, but you should always be using the UK National Annex. So let's have a look at what they are. So they are very similar. I should start by saying they are very similar to the values that are given in the Eurocode, but they do differ. So if you're ever thinking, oh, do I need to bother opening the UK National Annex? No, you absolutely should. And the argument for using these combination factors is if we're looking at one variable action at its full design value. So, for example, a wind, and it's in a storm, a 1 in 50 level storm. Is it likely that it's going to be combined with the full design value of another action? So that might be snow. And the answer is no. It's just not very likely at all. And the combination values psi naught gives you that sort of likelihood. So we start with the floor loading. We have 0.7 for residential and office buildings. We have 0.7 for shopping. And we have 1.0 for storage. So that's the only case where we actually do use the full design value, is when we're looking at storage. What does that mean? Or does this make sense? Yes, I think it does. It's just to say that a storage rack will commonly be used up to its full capacity. So in the event of that 1 in 50 year windstorm, is the storage rack likely to be full? Well, it could quite plausibly be full. So that's why storage has the higher value. We see for roof loading, again, 0.7, snow 0.5. So you can see that it's just about how likely are these combined actions to happen at the same time. So when we have different actions to consider, we need to look at each different load being the leading variable or the combined variable, and we need to test the combination and see which gives us the most onerous load combination. And there may be some instances where it's completely obvious by intuition, but I would suggest in most cases you need to just go through and check each different combination with the variable action being either leading or accompanying. So now here's a table which shows you how you would want to combine these partial factors using 610. And you'd have to basically go through each one of these for the load levels you have and find the governing load combination. So we start with floor load being the leading variable. When we combine that, we would combine it with wind. Well, in this instance, wind and snow. So I'm quite sure when you do that, it's quite unusual. But you see that we have gamma, the live load factor gamma q 1.5 multiplied by the combination factor 0.5, and that gives us a total of 0.75. And the combination factor 0.5 is the same for both wind and snow. So we end up with 0.75 for both of these actions. A perhaps more instructive example where we have wind as the leading variable, you can see that the combination factor for floor loading is 0.7. So we multiply that by 1.5 to get a total of 1.05. But snow again would be at the level of 0.75. So for each of these combinations, we need to test it with different action being the leading action, and then the other variable actions being accompanying, and then we need to find the governing load case, or load combination, I should say. So now we'll get on to the difference between equation 610 and 610A and 610B. So I described before that 610A and 610B will always give you design values that are lower than 610, and here's where we sort of demonstrate why. So looking at the difference between 610A and 610, the only difference is that we've introduced sine naught for the leading variable action as well. So that's to say we're going to use the sine naught value, which was, for typically 0.7 for an office. It might be 0.5 for wind or snow, and then only in the event of storage would it be 1. So we can see that if we compare these two equations, if sine naught is less than 1 or less than or equal to 1, the result is always going to be lower than 610. If we now look at the difference between 610B and 610, we see that the difference between the leading variable, that this is actually all identical. So the right-hand side, all the variable actions are identical. The only difference between 610 and 610B is the introduction of this xi factor. So the xi is a factor that reduces the permanent actions, the dead loads, and we take this from the UK National Annex, and it is a value of 0.925. So when we multiply 0.925 and gamma g, we that's 0.925 and 1.35, we get a value about 1.25. Note that the core Eurocode specifies this value at 0.85. That's not what we use in the UK, so you just need to be careful if you ever see that. It should be taken at a value of 0.925. Again, comparing it with 610, we see that 610B is always going to be lower. So the only difference is this factor, and it's less than 1. So in summary, we see that the use of 610A and 610B will always produce a smaller design value than the use of 610. I would suggest it's a minimal additional effort, and we'll get onto a couple of examples later. The saving may not be enormous, but once you add it up over a large area or over many stories, you could get a reasonable saving in both economy of the structure, tonnage, and of course carbon. So it's certainly something we believe is absolutely worthwhile. And say that also the saving that you get will depend on the relative proportions of the permanent actions to the variable. Now, if we look at a comparison between 610A and 610B, and we'll just look at a sort of the common case of an office floor where our combination value of sine naught is equal to 0.7. So for 610A to be greater than 610B, we can just apply all our factors and cancel out to give us the inequality that for this to be true, for 610A to be greater than 610B, GK, so the characteristic permanent action, needs to be greater than 4.5 times the variable action, QK. So if we say QK is typically something, let's say 2.5 kilonewtons per meter squared, that would mean that GK would need to be almost, 11 kilonewtons per meter squared. That's quite a heavy structure to carry quite a light load, certainly in the world of steel. So I would suggest that that's quite unlikely, and therefore that in the vast majority of cases, certainly for steel design, it will be 610B that will govern. You will of course have to check 610A, but once you've got a bit of experience using this, you'll find that 610B is pretty much always going to govern. Now we'll just go through a quick example, or a couple of examples. So the first example we're going to look at is just a simple floor. It's only got one variable action, which is live load or imposed load. We've got permanent actions are equal to 3 kilonewtons per meter squared. Variable actions are equal to 2.5 kilonewtons per meter squared. If we go through the various different equations that we have at our disposal, we'll start with 610, the sort of simple one. 1.35 times 3 plus 1.5 times 2.5 gives us a value of 7.8 kilonewtons per meter squared as our design value. So if we now look at 610A, we can see that we introduce the combination, the psi naught combination value at level of 0.7. That gives us a slightly reduced, well, quite a significant reduction. So we go from 7.8 to 6.7 kilonewtons per meter squared. And now if we look at the equation 6.10b, and we introduce our xi factor at a level of 0.925, we get a design value of 7.5 kilonewtons per meter squared. So of course, when we're looking at 610A and 610B, we have to take the worst case. In this instance is 7.5, as we might expect. And therefore, we can see that when we combine the worst case out of 610 and 610B, we see that we have a 4% saving compared to if we just looked at 610 alone. So it's not a huge case in this instance. If we looked at a structure that had a higher proportion of its load as the permanent actions or higher dead weight, we would find a slightly greater value. A slightly greater reduction. But as I mentioned before, it's 4%. That might be enough to just tip you into a slightly lighter beam choice. So it potentially could save you more than 4% steel weight. And yeah, I would suggest obviously in many instances these calculations are done by computer models anyway, so it's really minimal extra effort for a potentially useful saving. We're now going to look at the slightly more complex example where we're looking at a roof, and we'll see here we have permanent loads, we have snow loads, and we have wind loads. So depending on the slope of a roof, we'll often find that we have wind loads acting downwards, and therefore they are acting in the same direction as the snow load. And that's the example that we're going to look at here. You'll see that we have two variable actions, and therefore we need to check both of them as the leading variable action to ensure that we know which case is worst. So again, looking at equation 610 first, we have the first example. We'll look at snow as the leading action. So we have our permanent actions, our dead loads multiplied by 1.35. We have our snow at the level of 0.6 multiplied by 1.5, and then we have wind as our accompanying action, and therefore we used sine naught of 0.5. And that gives us a total of 1.28 kilonewtons per meter squared. Now we consider wind as the leading action. So we'll say here is the wind load, that's the leading action. And here we have the snow load, and we use it using the combination value. Therefore, we're using sine naught is equal to 0.5. We sum that up and we get a total of 0.95. So as you might predict, snow being the greater value action in this case, it was snow as the leading action, leading variable action, which is given again of us our governing load combination. So now we will look at the expression 610A and 610B again. I won't bore you with all the numbers again, but just to say that now when we use 610A, we introduce the psi naught for the main, the leading variable action again. And then when we look at 610B, we introduce the psi factor at a level of 0.925. So the governing expression of these two would be 610B again, and we see that it gives us a value of in this case 0.925, and it was in the previous example for 610 it was 0.95, so a very modest reduction in this example, but we would see greater benefit if we had a high proportion of dead load. So hopefully that's cleared up questions about the permanent and transient states. We'll now have a look at the accidental and seismic combinations. So here is the expression 611B from EN 1990, and this is the accidental load combination of actions. I'll just step through the different components again, going from left to right. So first of all, we see that we have the permanent actions. Now, the key thing to highlight here is that they are unfactored. So there is now no gamma G anymore. We've got the pre-stressing terms we're going to ignore, not very common for steel structures. We've got the accidental action, and again, this is unfactored. So we've got the unfactored dead, the unfactored accidental action, whatever that might be, and then that is combined with the variable actions. But you'll notice that we have the psi factors involved. So we have a choice in the core Eurocode of psi 1 or psi 2 for the leading variable action, and then for other variable actions we have psi 2. And the Eurocode is not completely helpful in this regard. It says that there is a choice to be made by the designer. Well, thankfully, in the UK, we have the UK National Annex to turn to, and that specifies that we should be using psi 1 for the main accompanying variable action. So that's the leading variable action in the accidental design situation. So if we go back, we see that actually in the UK, we should always be using psi 1. So thankfully, the UK National Annex has cleared that up. So if we now go back to table NA.A1.1 from the UK National Annex, we can see we have a range of different combination factors, psi 1 and psi 2, that we use in the accidental combination. And you'll see that these are at a lower level than psi 0. And just to give you a few examples, again, this is sort of looking at probabilities. What is the probability of a certain design load being, for example, on a floor, in the event of this accidental design situation? We want to consider, and therefore, it's less probable. Therefore, we want to look at lower, reduced variable actions. So here's the sort of final accidental load combination 611B when we sort of use it with the UK National Annex. So again, just to summarize, we have the unfactored permanent action, so unfactored dead load. We have the accidental action, again unfactored. We have the leading variable action at a load level using psi 1, and then we have accompanying variable actions using psi 2. So yeah, I think that's all clear. This sort of represents the fact that in the accidental load combination load case, we just want we want the structure to stand up, of course, but this is not a regular event. Therefore, we don't expect perhaps the additional margins of safety on, for example, the permanent loads. And again, it reflects the probability that in this accidental design scenario, would we expect to have the full, whatever it might be, occupancy? Probably not, and therefore this accidental load combination permits you to take that reduction. So let's just go over what a few sort of these accidental situations might be, because I think, as I alluded to before, they crop up more often than you might find. So there's a few sort of key accidental situations to consider. The first one is drifted snow, and I should highlight that this is this whole presentation is in accordance with the first generation Eurocode. So if you some of these things will not be true in a couple of years, and for that I can only apologize for the confusion. But at the moment we're focusing on the first generation Eurocodes, and in the first generation Eurocodes, drifted snow, so that snow that sort of accumulates in a valley or behind a parapet, that is considered a accidental design situation in the first generation Eurocodes. The result of this is that if let's say you're designing a portal frame with a parapet, you probably find that the main steel members will be governed by your fundamental design combinations. That's using load factors of 1.35 and 1.5 on the variable actions. But when you come to just perhaps look at the purlin design or the purlin spacing, these drifted snow load cases, even at the accident, when even considered with some no load factors, they can still govern the spacing or the purlin thickness, because you can get quite high concentrated loads. So that's drifted snow. The second thing, scenario where these accidental combinations should be used is when an opening is assumed to be shut, but it would have a major impact if it was open. So the Eurocode permits you to assume that if an opening can be expected to be closed, and then to assume that's no problem. But you should consider the case where it is still open, but that could be considered as an accidental design situation. So if you've got a dominant opening in a building, that will obviously lead to some quite high internal pressure coefficients, meaning that the building would want to sort of blow up, or inflate, I should say, or deflate. So you don't need to consider this for your main design combinations, your ultimate limit state design combinations, but you do need to consider it as an accidental situation. The final one is tying. We'll go into a bit more detail later, and these are combinations where we want to avoid the disproportionate collapse of a building due to an accidental action. And there are particular rules given for the load combinations in EN 1901 Part 1, Part 7. So just to round things out, I'm not going to dwell on this for too long, but we'll cover now the seismic load combinations, which is 6.12b. So we'll see that we have the unfactored permanent action, so unfactored dead load. We have accidental action, and then we have the accompanying variable actions. So we see that there's no variable action, no leading variable action, just accompanying, and all variable actions have the psi 2 applied. So that's essentially saying it's really like the quasi-permanent loading, and here's the range of values that are given in the UK National Annex. So we can see that quite intuitively, wind, snow, and roof loading, so typically access, they have no quasi-permanent component. But when we look at, for example, office or shopping, or more critically storage, we see that they have a higher proportion of the characteristic value could be considered quasi-permanent, and that needs to be considered in the seismic combination. So one very important clause to highlight from EN 1991 Part 1, Part 1 is this clause 3.3.2, the additional provisions for buildings. You'll see that we don't, on roofs, imposed loads and snow loads or wind actions should not be applied simultaneously. So that's to say, when we have the 1 in 50-year wind load, will there be people? Probably not. I suggest that's not the best time to be doing maintenance of a roof. And the same goes for when you have 1 in 50-year snow loads. And the Eurocode says that's unlikely, and therefore you do not need to consider it. So if we're looking at the combination of gravity loads, we need to look at the combination of permanent and imposed, permanent and snow, and then we need to pick the more onerous of the two. We do not need to consider permanent, imposed, and wind together, and we do not need to consider permanent, imposed, and snow together, but we do need to consider permanent, wind, and snow in combination, and we need to consider each one with either wind as the leading variable action or snow as the leading variable action. So that's the sort of summary of combinations. Now I'm going to touch on reduction factors. As I started mentioning at the start of the presentation, I would suggest that these things are absolutely should be used in reducing the load. You can save weight, potentially the size of a member, save cost, and of course carbon. These reduction factors, there's two different types. There are reduction factors for an area. That's to say, if you have a large floor or a beam supporting a large area of floor, what is the probability that the entire thing will be loaded to its full characteristic value? Perhaps, if it's a very large area, possibly not. And then we have reduction factors for stories. So what's the probability that the design load will be present on all stories at a certain time? So again, that's unlikely, and therefore we don't need to consider it. So for reduction factors by area, there is an expression that's given in the UK National Annex, and there's the expression here where A is the total, the tributary area of or the supported area, or perhaps by a beam, or and we see that this gives us quite good savings. If you're looking at a long span beam, this can be very helpful. And we also have a reduction factor for number of stories, again given in the UK National Annex. This one goes by the number of stories that you are considering. So if you're looking at the column at the base of a building, based on the number of stories that it is supporting, you are permitted to use this reduction factor, and you'll see that where the number of stories is greater than 10, this goes down to a reduction factor of 0.5. So you're considering 50% of your imposed variable load. So a really significant saving. We've got the plot of that function here. You can see that, yeah, as you get anything, really anything beyond 5 stories, you're getting quite a significant saving in the variable load that you need to consider. So yeah, I think that's certainly worthwhile considering. Certainly my time as a designer, we would absolutely always consider these area and story reduction factors. One thing to draw your attention to is that in 1991 Part 1 Clause 3.3.2, you are not permitted to combine the psi factors with the area reduction factors, or the story reduction factors. So you have to pick one or the other. But I think this is when if you're considering these as not the leading action, I would suggest that it's unlikely to make any difference to your calculations anyway. Quickly look at the serviceability combination of actions. There are 3 different levels to look at that we look at. We look at characteristic, frequent, and quasi-permanent. And the time that we need to use these different combinations is not actually specified in EN 1090 or 1991. It's actually given in the material standard. So if we go to the EN 1993 Part 1, Part 1, it doesn't really give us much information. It just says, you know, you need to agree them with the client, or specify on each project and agree with the client, but it points you to the national annex as where you may be able to find them. So we'll go to our UK national annex, and it says we need to consider the characteristic load combination, but only due to variable loads, and should not include permanent loads. So that's fairly straightforward. We need to, it's essentially saying you need to look at the full variable action. You do not need to look at the permanent loads. The suggested limits in the national annex are given as follows. I think everyone should be familiar with them. They are unchanged, going back to 5950 as well. So nothing particularly special to see here. So here we have the various SLS combinations. Again, we're told we need to use the characteristic, which is this top one. So, but if we make this sort of modifications as required by the UK National Annex, we see that actually it's just the combination of the leading variable action at its full value, and then the accompanying variable actions at their combined value. So that's usually like a factor of 0.7 or 0.5. I would suggest it's fairly unusual that you would need to combine variable actions for checking deflections, but if you need to do, that's how you would do it. But really what you're looking at is just the characteristic value of the variable action. Again, looking at horizontal deflections now, it's the characteristic load combination due to variable load. Again, we will now look at the suggested limits. And then again, they'll be familiar to everyone. They're the same as 5950. So let's quickly look on robustness now. So when we look at horizontal tying, there was rules in 1991 Part 1, Part 7, and they are endorsed by the UK National Annex. We see we need to use this combination of for internal ties. So we've got 0.8 multiplied by the dead load, and then we variable loads at the frequent level. There's a minimum value of 75 kilonewtons. So and for class 2 buildings above, we need to also consider vertical tying. So that means that what that really means in practice is that you need to design your splices for tension, and that can be quite onerous. Now, what I think this is one thing I in putting together or sort of reviewing the content of this presentation. One thing that I think may trip up a few people here, which is the combination of actions when we're looking at brittle fracture. So this is really important to look at. We're very clear at the SCI that it's the designer's responsibility to specify the steel subgrade. It's the designer that knows where it's going to be used. Obviously, the temperature. They know the state of the state of stress, and they know the thickness. So they are the sort of person involved in the design that has all the critical components required for the selection of subgrade. So if we go to table 2.1 of EN 1993 Part 1 Part 10, we see this this table, which gives us the reference, the minimum thicknesses, or the maximum thicknesses, sorry, I should say. If we go to the UK National Annex, we find that we're only actually allowed to use this portion of the table. So we need to use we need to know the design stress to ensure it's in the core Eurocode you would use a design stress to select one of these tables. In the UK National Annex, we only use this table. However, when there is an adjustment factor that's provided in the National Annex, the EN 1993 Part 1 Part 10, which this delta TR theta, And in order to calculate, to select the correct value of this, we need to know the design stress and as a proportion of the design yield. So the design stress is what we're going to focus on when we look at the design combination to be used for brittle fracture. Fy is a function of T. I'll summarize this now. So Fy is a function of T, is the design strength of the steel. In the Eurocode, there's two options. We can use this sort of straight line fit, which we start with your nominal and reduce it based on the thickness. But I would suggest, and with the SEI, we would always use the design strength taken from the relevant steel standard. I'm sure everyone's familiar with this, where you have steps in the design strength at 16 millimeters thick, 40 millimeters thick, 63 millimeters thick. So that's your design strength of the steel. The stress that we want to consider is the stress due to this combination here, where and we'll just go through this in steps. So first of all, we have the stress due to temperature change. So depending on the structure, that will commonly be 0 if we've got we've got room for the structure to move. It's free to move, and we've got bolts in, for example, in clearance holes. We have the unfactored permanent actions, and then we have the variable actions at a reduced design level. So the key thing to highlight here is that the stresses that we're considering for brittle fracture are less than SLS. So if you we'll go through an example later, so that should hopefully clarify that. So we've been through this. This is the design center of the steel. We're going to look at an example here. We've got a restrained floor beam spanning 7.5 meters. It's got an office usage case. Permanent actions 21 kilonewtons per meter and variable actions 24 kilonewtons per meter. So our design value for designing the steel would be 64 kilonewtons per meter. Design bending moment 450 kilonewtons meters. Let's pick this beam here, a UB 457 by 191 by 67 in S355. We find that we've got bending resistance of 522 kilonewtons per meter. So we've got a bit of room to spare there. We first check our deflection. Deflection of 16 millimeters, and our allowable is going to span over 360, 20.8 millimeters. So therefore, we're meeting that check. We now check the state of stress using the combination described before. We've got 21, the unfactored permanent load, 21. The reduced variable load, 0.5 times 24 is 33. That really gives us a bending moment of 232 kilonewton meters, a stress of 158 newtons per millimeter squared. Our flange thickness is 12.7 millimeters. So that's less than 16 millimeters, so that we know we have the full 355 newtons per millimeter squared yield strength as our design strength. And then we take our design stress over our design yield stress, 158 divided by 355. We find that proportion is 0.45. So just to highlight that we would expect this always to be less than 0.5, and for most, all common design situations. If you're looking at brittle fracture and you got a design stress over 0.5, then I would suggest you need to just make sure you're using the correct load combination. And I've suggested here that 0.3 is something would be perhaps more typical. So for brittle fracture, if fatigue is a design consideration, you should be using Eurocode and the UK NA. If fatigue is not a design consideration, which will be obviously the majority of steelwork in the UK for buildings, we suggest you look at P41, the SEI publication P419. That applies all the UK national annex rules, but it removes some of the fatigue crack growth, and that gives you some increased thickness limits that you'll find are very beneficial. So that's a topic for another presentation, but that's a very helpful publication. Just touching before we get onto the crane, because I noticed we're short on time now. Just a few considerations for designing to ensure that we're producing the most economical and also structures with the least embodied carbon. When you're choosing your variable actions, I would suggest you use the code minimum, and you don't specify anything higher. So in the past, we used to see a lot of offices designed for 5 kilonewtons per meter squared. Suggest that that's probably not necessary. Same for movable partitions. There are some reduced values that you can find in the Eurocode. We suggest that you always use the area and story reduction factors. We suggest that you use the more onerous of 610A and 610B. It's a minimal extra effort for potential saving, and we would also suggest you use S460 high strength steel for columns. Right, quickly, just to wrap up now, because I noticed we're short of time. We're going to look at the example of a crane. We've got 2 examples of cranes here. We've got an overhead crane shown on the left in a building, and an underslung crane on the bottom flange on the right. Now, a quick summary would be that actions on cranes or actions due to cranes it's really quite a complicated design process. You have lots of different types of actions to consider, and then you have lots of different dynamic factors that they need to be multiplied by. So actions on a crane, the up and down, left and right, so to speak. You got different, picking things up, putting things down, hitting the buffers. For each of these different types of effect, you've got a different dynamic factor to apply. If we go to table 2.2, we'll see how these different dynamic factors and different actions of the crane need to be combined. All is to say, it's quite complex. There's lots of different things to consider. Not straightforward by any means, and often you'd be better off using software to find the governing load cases. If you're interested, or if you're doing this, we would recommend this worked example shown on screen. If you Google worked example crane supporting structures by Sedlacek, you'll find this, and we would suggest that this will go through all of the loads, all the different dynamic factors, and helpful to have it by your side, whether you are designing looking at crane actions for the first time, or indeed the 10th. So even after you've applied all your dynamic factors, the crane actions that the result are still the characteristic unfactored values, and they must be combined with other actions, and therefore we must combine them using the design combinations that we looked at previously. The recommended values for the partial factors, so that's gamma G and gamma Q, are given in table 8.1, but also they are set by the national annex. So this is perhaps the slightly surprising thing, or certainly to me, the first time I looked at this. If we go to table 8.1, we see that we have our partial load factor applied to our permanent actions is 1.35, so that's as we might expect. But when we look at the variable actions due to the crane, we would find that we have a partial factor of 1.35. So the first time you might see this in a worked example, you might think, is this a mistake? For every other variable action, we would expect to multiply by 1.5, but no. In the Eurocode, it's given as 1.35, and indeed, it is also given in the UK National Annex. So I skipped ahead a bit there, but you find that the gamma values are to be taken from the core Eurocode. I'll skip back now. When we look at combinations, and when we're looking at the combination level, gamma naught for crane is taken as 1.0. And again, that is accepted by the UK National Annex. So in summary, that's all to say that when you see this 1.35 being applied as to the variable actions due to a crane, that is not a mistake. That is given in the core Eurocode and indeed also endorsed by the UK National Annex. So with that, I'll say thank you all for joining, and I will speak to you hopefully in a couple of weeks.